Good day, students. Today, let us look into an application of Fresnel diffraction. Let us see the working of a zone plate. Now, the zone plate is actually a pattern, as shown on the right side, drawn on any optically transparent material. Okay. Now, this device can be used to focus light or any other electromagnetic waves like X-rays or microwaves. Here, light is focused by using the phenomenon of diffraction. In lenses or in mirrors, light is usually focused by refraction of light or by reflection of light. Here, the zone plate makes use of the phenomenon of diffraction to focus light. Now, here, on a glass plate, several concentric rings are drawn on it with the radius of the ring proportional to square root of n natural numbers. Now for the first ring, we have the radius proportional to root 1. And for the second ring, we have the radius proportional to root 2. And for the third ring, we have the radius proportional to root 3. Okay. So on these points, we draw concentric circles. After drawing that, we get intermediate zones. So this will be the point of R1, this will be the point of R2, R3, R4, R5, etc. Now R1 will form a region and this is called the first zone. And the area between the R1 point and R2 point is called the second zone. Likewise, we have several zones that are formed in the concentric manner. Now these rings form zones that alternate between opaque and transparent and are spaced so that light transmitted by the transparent zones constructively interfere at the desired focus. Now we have zones and they are alternately made into opaque or transparent regions. So here the first zone is made opaque, the second zone is transparent, third is opaque, fourth is transparent. So here all the odd numbered zones have been opaque and the even numbered zones have been transparent. The either way can be done. That is, the odd zones can be made transparent and the even zones can be made opaque also. Now, let us look into the types of zone plates. The first one is the positive zone plate. When the odd zones are kept transparent to light and even zones are made opaque to light, then it is called a positive zone plate. And the pattern is shown here. All the odd numbered zones 1, 3, 5, 7 are all transparent and the even numbered zones 2, 4, 6, 8, etc. are made opaque. So light will pass only through the odd numbered zones and hence the amplitude due to the positive zone plate RPZ on the screen is equal to amplitude from R1 from the first zone R1, amplitude from the third zone R3, amplitude from the fifth zone R5 plus etc. So all the amplitudes from the odd zones will add up and this is definitely greater than R1 by 2. Now in the next type of zone plate, it is called the negative zone plate. Here, even zones are kept transparent to light and the odd zones are made opaque. Hence, light passes through the even zones and the amplitude due to the negative zone plate RNZ on the screen is equal to R2 plus R4 plus R6 plus etc. very much greater than R1 by 2. So in both the cases, positive zone plate and negative zone plate, the amplitude has increased substantially. We say this because in the earlier discussion of the Fresnel half-period zones, we found out that the amplitude on the screen due to the Fresnel zones is approximately equal to R1 by 2. And in order to increase the amplitude on the screen, we can make the zone plates where alternate regions are made opaque and the resultant amplitude will be much greater than R1 by 2. Now in the next type of zone plate, the phase reversal zone plate, alternate zones of the zone plate are coated with a thin film such that it produces an additional path difference of half wavelength between the waves of successive zones. And this zone plate is called the phase reversal zone plate. Bring into mind the earlier discussion, we said that for a Fresnel wavefront or Fresnel half-period zones, the phases of light from each zone will be inverted. Now to again invert the phases, we produce an additional path difference of half wavelength, that is by coating a thin film of thickness lambda by 2 on the alternate zones. We produce an additional phase difference of pi, and hence all the zones will have light coming in the same phases. Thus, the amplitude from the phase reversal zone plate will be given by R1 plus the phase from R2 is reversed by the thin film. We have plus R2, then plus R3, then plus R4. The phase is reversed in the alternate zones R2, R4, R6. And hence, if we calculate the sum, it will be twice that of the amplitude from the positive zone plate, and that too twice that from the amplitude of negative zone plate. If the amplitude is twice, the intensity of the light that we see on the screen will be 4 times. Hence, the pattern on the screen will be of greater intensity in a phase reversal zone plate. Now let us mathematically try to derive the theory of a zone plate that explains how zone plate functions as a convex lens. Now in this figure we can see that when a source is placed in front of the zone plate, light from the source is focused to a point here. Now to understand this, let us draw a figure representing it. Now let the direction of the light be represented by the optic axis SOP and the zone plate be represented by OMN. Let the radius of each zone on the zone plate be represented by R1 radius of the first zone by OM1, then R2 radius of the second zone by OM2, and R3 radius of the third zone by OM3. Now from this figure, let me write SO plus OP is equal to A plus B, where A is the distance of the zone plate from the source and B is the distance of the zone plate towards the screen. Right. Now here we are going to calculate these paths SM1P, SM2P, SM3P and finally SMNP. For that, now let us find the distance of SM1 plus M1P. So SM1 plus M1P can be written as A plus B plus lambda by 2. Okay. So the point M1 is always drawn at a distance of B plus half wavelength. Likewise, M2 plus M2P can be written as A plus B plus 2 lambda by 2. Hence, SMN plus MNP can be written as A plus B plus N lambda by 2. Here by geometry, let us use the Pythagoras theorem to write Smn square is equal to A square plus Rn square, radius to the nth zone. Likewise, MNP square is equal to B square plus Rn square. Hence, in order to get this equation, we are going to write A square plus Rn square the whole raised to 1 by 2 plus B square plus Rn square the whole raised to 1 by 2 is equal to A plus B plus n lambda by 2. Right? Here we know that the distance from this point to Mn is A, and from this point to P is B plus n lambda by 2. And hence we have written it likewise here. Now we are going to expand this equation, and in the expansion we will be using an expression 1 plus x the whole raised to n is equal to 1 plus nx if x is very much smaller than 1. Now for that, let us do some rearrangements and substitutions. The equation can be rewritten as taking a outside, a into 1 plus Rn square by a square whole raised to 1 by 2 plus taking b outside, b into 1 plus Rn square by b square whole raised to 1 by 2. This is equal to a plus b plus n lambda by 2. Now using the expression 1 plus x the whole raised to n is equal to 1 plus nx, we can write a into 1 plus Rn square by 2a square plus b into 1 plus Rn square by 2b square is equal to a plus b plus n lambda by 2. This can be written as a plus Rn square by 2a plus b plus Rn square by 2b is equal to a plus b plus n lambda by 2. Here we can cancel out a on both sides of the equation and b on both sides of the equation. Hence we get Rn square by 2 into 1 by a plus 1 by b, and this is equal to n lambda by 2. Again we can cancel out 2. Thus we write 1 by a plus 1 by b is equal to n lambda divided by Rn square. Now by applying sign convention here, the distance from the point O towards the right is taken as positive and the distance from O towards the left is taken as negative. Hence, B will remain positive whereas A will become negative. This equation thus becomes 1 by B minus 1 by A is equal to n lambda divided by Rn square. Now this is very much similar to the length equation 1 by V minus 1 by U is equal to 1 by F, focal length of the lens. Hence, we can write that this term 1 by B minus 1 by A is equal to 1 by F is equal to n lambda by Rn square. That is, the focal length of the zone plate is equal to Rn square by n lambda. So from this theory we infer that the zone plate also acts as a converging lens and the focal length of the zone plate is given by Rn square by n lambda. Now let us look into the multiple foci of a zone plate. A convex lens has only one focal point, one focus, whereas a zone plate can have multiple focal points and hence multiple foci. Now in the expression of 1 by b minus 1 by a is equal to 1 by f, that is equal to n lambda by Rn square. Now if the source is at infinity, a becomes infinity, 1 by infinity will be equal to 0. So at a equals infinity, we have 1 by b is equal to 1 by f is equal to n lambda by Rn square. This implies that the focal length is equal to b, that is equal to Rn square by n lambda. Now this position of b, the distance of that zone plate towards the screen, that is the principal focus of maximum brightness. Now here, for the nth zone, the focal length is given by Rn square by n lambda, and the area of the nth zone is equal to pi b lambda, and radius of that nth zone is given as nb lambda. Now let us take a case where the distance b is reduced to b by 3. Now if we bring the screen closer to a point b by 3, 1 by 3rd times that of b, the radius of the half period zones, that too will increase. It becomes Rn prime is equal to 1/3 of the earlier value, Rn by 3, that is nb lambda by 3. And area also reduces, the area of that zone also reduces. It becomes 1/3 of the earlier value, that is equal to pi b lambda by 3. This means that each zone becomes 1/3 of its size. Each zone has reduced its size to 1/3 of its earlier value. So the amplitude from the first zone, R1 earlier, will be now the sum of R1 prime, R minus R2 prime plus R3 prime. The amplitude from the first zone earlier will now be the amplitudes from three zones. Three zones have entered into that region. Likewise, R2 will be R4 prime minus R5 prime plus R6 prime. Okay, here we understand that R1 prime is actually 1/3 of earlier R1. R2 prime is actually 1/3 of earlier R2. R3 prime is actually 1/3 of earlier R3. Likewise, R4 prime is 1/3 of earlier R4. R5 prime is 1/3 of earlier R5. R6 prime is 1/3 of earlier R6. Okay. Now the zone plate, okay, actually the zone plate allows light through R1 and blocks the light through R2. Alternate zones are allowing light and alternate zones are blocking the light. Okay. Only the screen is shifted forward, the zone plate behaves as such. So only light from R1 passes. Only this light passes, whereas this is blocked. And the contribution due to R3 will be R7 prime minus R8 prime plus R9 prime. They will be allowed, whereas the next contribution R10 prime minus R11 prime plus R12 prime, that will be blocked. Okay. Hence, we can say that the amplitude on the screen at b by 3 is given as, we have R1 prime minus R2 prime plus R3 prime, then plus R7 prime minus R8 prime plus R9 prime, etc. Now let us do a shuffling. R1 prime can be written as R1 prime by 2 plus R1 prime by 2, just making it into two halves. Now the next term, R2 will be average of R1 and R3. Hence, R1 prime by 2 minus R3 prime by 2. Now R3 is again written as R3 prime by 2 plus R3 prime by 2. Now R7 prime can be written as R7 prime by 2 and R7 plus R7 prime by 2. Now R8 prime can be written as average of R7 prime and R9 prime. Likewise, the term goes. Now here these two terms cancel out, these two terms cancel out, then these two terms cancel out. Likewise, and hence we will get half of R1 prime plus R3 prime plus R7 prime plus R9 prime, etc. So at this position again we get a higher intensity, and hence this point acts as the other focal point and it is called F3. It will be 1/3 times of the earlier principal maxima, and it is given as Rn square by 3n lambda. We have similar cases where B is equal to B by 5. The focal length is F5 is equal to F by 5, that is Rn square by 5n lambda. And when B is equal to B by 7, focal length is F7 given by F by 7, that is equal to Rn square by 7n lambda. So for a zone plate we have multiple focal points. It is illustrated in this picture. So here we have the zone plate, and the zone plate will have the principal maxima at this point. Okay, this is the position of the principal maxima, and hence it is given the order 0. Now if we move the screen towards the zone plate, we have other points where again light is focused. If we move the screen away from the zone plate also, we will see other focal points, and they are ordered as such here. Now in this picture we see that the zone plate, it produces different focal points. Okay. Now the 0th order represents the parallel beam of light that is passing through. So we'll see light as such. But if we place the screen at this point initially, we will get an intense beam here. And this is the first order focal point where n is equal to 1. And if we move closer, we have another point of maximum brightness. This is a second order focal point, the next focal point. And in order to view each point, what we do is we place a pinhole at this point, and hence we can remove all the light from the other points, and only light from this cone will pass through. It is shown in this picture. If we place a pinhole at that particular focal point, only light from that cone will pass through it. And if we place the pinhole here, only light from that cone will pass into that. Now, we saw that the zone plate also acts as a convex lens. Hence, both of them have similarities and both of them have dissimilarities also. Now, both the zone plate and convex lens are dependent on the wavelength of light. The dependence is shown here. Focal length of the zone plate is inversely proportional to wavelength, whereas focal length of the convex lens is proportional to wavelength of light. Both of these optical elements have the lens formula For the zone plate, it is 1 by b minus 1 by a is equal to 1 by f focal length, whereas for the convex lens, it is 1 by v minus 1 by u is equal to 1 by f, where v is the distance towards the image, u is the distance towards the object, and f is the focal length of the lens. Now, the real image in both of them is formed on the opposite side of the object, and the magnification of the image is given by b by a for the zone plate and v by u for the convex lens. Now let us look into the dissimilarities between the zone plate and convex lens. Now the convex lens has only a single focal point, whereas the zone plate has multiple focal points. Now in the convex lens, all the rays will travel the same optical path, whereas in the zone plate, there is a path difference between the rays from each half period zone. They differ by a path difference of lambda by 2. Now if we compare the intensity of the images, the intensity of the image formed by the lens is much greater than that formed by the zone plate. Intensity of the image of the zone plate is less than that of the intensity of image by the lens. Now in this picture on the right side, we see the structure of a Fresnel zone plate. And the distance between each zones here will come only in the dimension of a few micrometers. This can act as a converging lens. That's all for today's class. Thank you.